Hello everyone, welcome to my video on rectilinear motion. So we saw in the previous video how to anti-derive functions. So let's apply that. Let's take a look at some examples in physics. So rectilinear motion, what we're talking about is objects moving in basically in a straight line. And we saw in calculus 1 that if you're given the position function, so we called it s of t, and we take the derivative, so we're back to the derivative with respect to t, with respect to time, that gives us velocity, which we denoted as v of t. And if we took the derivative again, we get acceleration, which we denoted as a of t. Well, now if we're doing antiderivative, this means that if we're given the acceleration function and we take the antiderivative, well, that gives us the velocity. And again, if we take the antiderivative of velocity, what does that give us? It gives us the position function. Okay, so this is what we're going to look at. We're going to look at examples pertaining to rectilinear motion. Let's consider an example. So if we have the acceleration on Earth, it's 9.8 meters per second squared. Let's call it a. Well, since it's in the downward direction, because acceleration is downwards, it would be negative 9.8 meters per second squared. But let's call the acceleration a of t just the number a, some value a. Okay. And let's antiderive to go get the velocity function. So if we take the antiderivative of a constant, a, so a is a constant, what do we get if we're antideriving with respect to t? Well, we saw in the previous example, if you had the the antiderivative of 4 gave us 4x. Well, here the antiderivative would give us a times parameter t. Instead of x, we're using the parameter t, so we get a times t. And since we're antideriving, we know from our theorem that we have to add a constant. But in this case, the constant ends up being the initial velocity. So we call it specifically v of 0. This is the initial velocity. Okay. Velocity. So essentially, if you throw a ball up in the air, the force that you're using, or the velocity of the ball the second it leaves your hand, that's your initial velocity. And this is the velocity function. And now if you want to find the position or the displacement function, we use s of t, not d. S of t. And how do we get that? Well, we antiderive again with respect to t. So if we antiderive here, we get a, which is just a constant, so we leave it. The t becomes t squared, so we add 1 to the exponent and then divide by that value. And do the same thing here, v of 0. That's just a constant, so we'll keep the constant in the front and we multiply by t. Again, we can think of it as x to the 0 or t to the 0. And we're using the power rule for antiderivatives, so we add 1 to the exponent and divide by 1, giving us just t. Or you could just memorize when you're taking the antiderivative of a constant, essentially you just multiply by the variable you're antideriving with respect to. And we get a constant. Okay. But this constant again has a specific meaning. This constant ends up being the initial position. Okay. And we call it SO. And this is a well-known equation that we see in kinematics in secondary 5 physics, where we have a times t squared over 2 plus the initial velocity times t plus s0. Okay, this is an equation we're going to use in wood problems, which was derived from using the acceleration that we assumed was a and anti-deriving twice with respect to t, giving us this formula here. Okay, so let's go ahead and look at a couple of examples. So the next example over here, it says a particle is moving in a straight line. They want us to find the position function s of t of the particle, given that its velocity function v of t is equal to 4 sine t minus 2 cos t, and they tell us that the initial position s of 0 is equal to 0. So this is similar to what we saw in the previous video, but instead of using f of x and finding the original function, we're using v of t and anti-deriving to go get s of t. So let's go ahead and do that. So we know the antiderivative of the velocity is the position function, so we're going to antiderive. The antiderivative of 4 sine t is negative 4 cos t. So the derivative of sine is cos, but the antiderivative of sine is negative cos. So be careful with your signs. And the antiderivative of cos, 2 is a constant, so we can just sit in the front. Antiderivative of cos is sine of t. Okay, and since we're anti-deriving, we have to add a constant. We'll call it S0. Okay. So now we could apply our initial condition, S of 0 equals 0. So this is telling us that when t is 0, our S of t is 0. So we get 0 equals negative 4 times cos of 0 minus 2 times sine of 0 plus S of 0, our constant. So what we have to do is solve this. We get negative 4 times cos of 0. Cos of 0 is 1. So we get 0 equals negative 4 times 1 minus 2 times sine of 0, which is 0. That's 0. This is 1. So that's minus 0 plus S of 0. Negative 4 minus 0 is negative 4. Bring it over, it becomes positive 4. So we get 4 equals S0. So the position function, S of t, is given to be negative 4 cos of t minus 2 sine of t plus 4, because S0 is equal to 4, our constant. Okay, so this is like finding our particular solution. Okay, and this is the answer. We're done. Let's look at a couple more examples. So in the next example over here, we have a particle which is moving in a straight line, and it asks us again to find the position function of the particle, given the acceleration a of t is equal to t squared minus 4t plus 6. And they also tell us that S of 0 equals 0 and S of 1 equals 20. So as always, pause the video, try to solve this on your own, see if you're able to get it. So here we have two initial conditions. We know that the antiderivative of acceleration is velocity. So v of t is equal to, here we antiderive t squared, giving us t cubed, add 1 to the exponent, divide by that number, t cubed over 3 minus 4, add 1 to the exponent, so 1 plus 1 is 2, divide by that number, 2, plus 6t. And don't forget to add your constant. In this case, we're talking about the initial velocity, so we could call it v0. Okay, so this is our first equation, but here the two initial conditions that are given are in terms of the position function. So let's go ahead and just antiderive to get the position function, st. So the antiderivative of t cubed over 3 is t4 over 12, minus 4 over 2 is just 2, so we have 2t cubed over 3. Here we have plus 6t squared over 2, plus the initial velocity times t, and we have to add our constant, which in this case is plus S0. Okay, so we have our two constants to go find. We have to go find our v0, the first constant, and the second constant is S0. Okay, so let's go ahead and do that. First, let's use the first initial condition, that S of 0 equals 0, to find your S0. So that means that t is 0, S of t is 0. Replacing it, you get 0 to the 4 over 12 minus 2 times 0 cubed over 3 plus 6 over 2 is just 3, so I'm going to write 3 times 0 squared plus v0, which we don't know, but it's multiplied by the time, which we're replacing with 0, so that's gone, plus S0. Notice they all have 0, so they all cancel, and we're left with S0. So the constant S0 is essentially 0. So we use the first condition, that's done. Now let's go ahead and apply the second initial condition. So I'm just going to erase this, get this out of the way. And now we're applying the fact that S of 1 equals 20, so we're replacing t with 1, and we're replacing S of t with 20. Okay, so we get 20 equals 1 to the 4 over 12 minus 2 times 1 cubed over 12, over 3, plus 6 divided by 2 is 3 times 1 squared, plus v0, which we're looking for, and t is replaced with 1. And S0 we solved before was 0, so I'm not going to put it. I'm just going to look for my v0. So this gives us 20 equals 1 to the 4 is 1 over 12. It's just 1 over 12. Minus 2 times 1 cubed over 3 is just 2/3. Plus 3 times 1 squared is just plus 3. And plus v0. Okay. So let's go ahead and find this. Let's find the common denominator for each. The common denominator in this case, 12, 3, and 1 would be, all of them is 12. So the 1 over 12 will leave. 2 over 3, we're going to multiply the top and the bottom by 4, giving us 2 times 4 is 8. And 3 times 4 is 12. Okay, and here we're going to multiply the top and the bottom by 12. 3 times 12 is 36. and on the bottom we just have 12. Okay, so we have 1 minus 8 plus 36. That gives us 29 on 12. So 20 equals 29 on 12 plus V0. We're going to subtract the 29 on 12, giving us, let's use a calculator, 20 minus 29 on 12, 211 on 12. So the initial velocity, V0, is 211 on 12. Okay, so the position function is t to the 4 over 12 minus 2t cubed over 3 plus 3t squared. 6 divided by 2 is 3. Plus V0, which we just found. V0 is 211 on 12. So 211t on 12. And we know S0 was 0. We solved that before. So this piece is gone. And this is our final answer. Okay. So that's done. Let's keep going. So in this example over here, we have a rock which is dropped off a bridge 490 meters above the ground. So we drop our rock. We want to find the height after t seconds. So let's go ahead and do that. So the height is essentially the position. We want to find the position after t seconds, but we don't have much information. All we know is that it's dropped off a bridge which is 490 meters above the ground. That's the height of the bridge. So we have h, height, but that seems to be it. This is happening on planet Earth, so we're assuming acceleration to be 9.8 meters per second squared. Okay. Another thing, just be careful. You're working in meters here, so make sure that it's 9.8 meters per second squared. If you have to use feet, make sure you convert appropriately. The other thing is because acceleration is in the downward direction, we put a negative in front. So the acceleration in the downward direction, the gravitational force is negative 9.8 meters per second squared, and we want to find the height after t seconds. So using the fact that a is equal to negative 9.8, we could construct this this formula again. We could either use the formula for memorization or we could reconstruct it. So I'm going to go ahead and reconstruct it. Use the fact that a of t equals, in this case, negative 9.8. I'm just going to plug in the value right away. And we're going to antiderive the acceleration to get velocity, and then antiderive once more to give us the position function, which is essentially the height. So antideriving the first time, we get negative 9.8 times t plus a constant. In this case, it's the initial velocity. And should we stop here? Let's antiderive once more to get the position. So if we antiderive again, we get negative 9.8 t squared over 2 plus v0 times t plus our initial position. Okay, so to figure out the rule, we're almost done. All we're missing is v of 0 and s of 0. That's the only thing that's missing from our rule. Negative 9.8 divided by 2 is negative 4.9. So we can write negative 4.9 t squared. The initial velocity, we have to understand the situation that's going on. What's the initial velocity of the rock? So if it's on my hand and I drop it, what's in that split second when I let go, what's the velocity of the rock? Since it's leaving my hand at rest, it's 0. So our initial velocity, v0, is equal to 0. They essentially gave us an initial condition by telling us that the rock is dropped. I'm not throwing it downwards, making it go faster. It's leaving my hand. So as soon as I let go, it's dropped out of my hand. Its velocity in that moment, the initial velocity is 0 meters per second. Okay, so this piece here is out. 0 times t, you take it out. Okay, so there's no initial velocity, v0 is gone. And what's the initial position? Well, since we're dropping it from a cliff, we are 490 meters above the ground. So the rule is plus 490. And this is our equation. S of t equals negative 4.9 t squared plus 490. Let's look at the next part of the question. So same question, now it's asking how long will it take the rock to hit the ground? Okay, so what information are they asking us really? Well, they're talking about the position of the rock. They're saying it's going to hit the ground. So what they're really giving us is the fact that your S of t is equal to 0. Because the position of the rock, if the bridge is 490 meters above, then the floor or the ground is at 0. So they're telling us that the final position, S of t, is equal to 0. And we're looking for the time. How long will it take? Okay, so this is asking for t. So we use the rule that we got in part A. So S of t equals negative 4.9 t squared plus 490. Oops. 490. We're replacing our S of t with 0 and we're solving for t. So it's essentially just a quadratic. Negative 4.9 t squared plus 490. We could factor out the negative 4.9 and use difference of squares, but I'm just going to bring this over. It becomes positive 4.9 t squared equals 490. Divide by 4.9. So this gives us t squared equals 100. Right. If we multiply 4.9 by 100, we move the decimal twice. It gives us 490, so this is fine. And the last step is to square root both sides, giving us the time equals plus minus 10. So we're square rooting a number, it gives us two values. But since we're talking about time and we can't go back in time, technically, we're only considering the positive case. Okay, so t equals 10. And that's the answer. So it's going to take 10 seconds for the rock to hit the ground when it's dropped from a cliff or a bridge 490 meters above the ground. Let's keep going and look at the next part to the question. So the next part of the question says, what was the velocity the moment the rock hits the ground? Okay, so we need the velocity function. We actually solved for it already. I just erased it. But we started with the acceleration, the fact that the acceleration is negative 9.8 meters per second squared. I'm not using units in here. And we took the antiderivative, giving us the velocity. So the velocity equation that we got was v of t equals negative 9.8 t plus v of 0. Right? So now it's asking, what was the velocity the moment it hit the ground? Well, when did it hit the ground? In part B, we figured out that it hit the ground after 10 seconds. So we have to replace our t with 10. But there's an issue. What's our v0? Well, we said this already. The v0 was, since the rock was released at rest, the initial velocity is 0. So v0 is gone. We don't have to include that. We just have to substitute t with 10. So this gives us negative 9.8 times 10, which is equal to negative 98 meters per second. And that's the velocity of the rock when it hit the ground. So it's negative because we're going in the downward direction, so it makes sense. And it's with a speed of 98 meters per second. Good. So this is the answer. Let's move on to the next part of the question. So the next part of the question says, if the rock is thrown downwards with a speed of 5 meters per second, then how long will it take to hit the ground? So instead of dropping it, we're throwing it downwards now. So how does this change and what do we expect the time to be? Well, by releasing it, we know that the time took 10 seconds to hit the ground. So by throwing it downwards, we would expect for it to be less than 10 seconds. So let's go ahead and see if we could find the answer. So we have to create the equation again. It's a new equation now because it's a different situation. So a of t, we're still on planet Earth where the acceleration is negative 9.8 meters per second squared. We antiderive, giving us negative 9.8 times t plus our initial velocity. But now we have an initial velocity. It's a speed of 5 meters per second. And since we're throwing it downwards, its velocity in the downward direction, it's going to not be 5. We're going to use a negative 5. Okay? Because we're throwing it in the downward direction. If we would have thrown it upwards, then it would have been positive. Okay? So keep that in mind. And now we're going to take the acceleration. Sorry, we're not going to take the acceleration. We're going to take the antiderivative of velocity to give us the position, to figure out how long it took for it to hit the ground. So S of t equals negative 4.9 t squared. So you add 1 to the exponent, giving us t squared, and then you divide by 2. So negative 9.8 divided by 2 is negative 4.9, as we saw earlier, minus 5t plus the initial position. Okay. The initial position, it's the same question, it's the same cliff that we're using, so it's still 490 meters. Let's replace that. And now we have to solve this over here. So in order to solve this, you have to use quadratic. Because we're using large numbers and we have decimals, quadratic is probably the way to go. Trying to use factoring techniques when you have decimals or very large numbers is difficult. So often I encourage you to use factoring methods, difference of squares, product sum. But in this case here, since we have large numbers and decimals, quadratic is the way to go. So let's go ahead and solve this using quadratic formula. The S of t, remember, because we're trying to see when it hits the ground, it's 0. So we're really solving the equation 0 equals negative 4.9 t squared minus 5t plus 490. Okay, so let's use quadratic. We'll call it T1, T2. So it's negative b plus minus the square root of b squared minus 4ac over 2a. So I'm just going to erase to give myself some room. So in this case here, our a is negative 4.9, our b is negative 5, and our c is 490. So negative of negative b, it's positive 5 plus minus. So be careful with the double negatives. The b here is negative 5. So here it's negative of negative 5, giving us positive 5. Square root of b squared, so negative 5 squared. Minus 4 times a is negative 4.9. And then times c, which is 490. All this divided by 2a, so 2 times negative 4.9. Let me erase this. So what we get is 5 plus or minus the square root of 25. Negative 5 squared is 25 minus, actually there's two negatives, so it's going to become positive. 4 times negative 4.9 times 490. I'm getting 9,604. All this divided by negative 9.8. Okay. Plus 25 square root. So this gives me about 98.12, 0.13. So this answer plus 5 divided by negative 9.8. So my first answer is negative 10.52. Remember, this is time 1. And our second time, if we subtract square root of 25 plus 9604, five minus this answer divided by negative 9.8. Time 2 gave me about 9.5 seconds. Okay, so obviously we're talking about time, so we can't have a negative value, so we reject that answer. And t2 equals 9.5. Again, that makes sense because adding velocity, it's going to hit the ground faster, so we save 0.5 by adding an initial velocity. Okay, so after 9.5 seconds, it's going to hit the ground, and that was the question, so we're done. Okay, so let's take a look at another example. So in the next example over here, we have to find how high the cliff is, knowing that a ball is dropped off it and hits the ground with a velocity of 128 feet per second. So the first thing you have to be careful for is the units. We're working with feet, not meters. And the other thing is we're looking for the height of the cliff, so the position. And all they really give us is just velocity. So how are we going to do this? We begin with the acceleration. Since this is happening on Earth, we assume the acceleration to be negative 9.8 meters per second squared. But again, be careful with the units. It's not meters, we're working with feet. So negative 9.8 meters per second squared is about negative 32 feet per second squared. Okay. Now, we have the acceleration. Let's go find our velocity function by anti-deriving with respect to t. The antiderivative of negative 32 is just negative 32. Since it's a constant, we're just going to add a t times t plus the initial velocity. Okay, and let's anti-derive again to get the position, because it's asking for the height of the cliff, so we want the position function. Anti-deriving once more, we get negative 32 t squared over 2 plus v0 times t plus the initial position. Okay, so this is the formula that we saw earlier. You could have just jumped straight to the formula and then plug in what you know. What information is given based off the problem? So it's asking how high the cliff is. The ball is dropped, that's important, and it's telling us that it's hitting the ground with a velocity of 128 feet per second. So sometimes it's good to do a quick sketch. If this is the ball, up here it's being dropped and it's hitting the floor down here. What do we know? Well, we know the initial velocity of the ball, v0, is 0 because it's being dropped, it's being let go. And what's the initial position? The initial position we don't know. That's the height of the cliff, that's what we're looking for. But what do we know at the bottom of the cliff? Well, we know the position, let's call it S final, is 0 because that's the floor, that's, let's say, ground 0. And the the velocity when you're hitting the ground is given to be 128. So the V final is since it's going downwards, the velocity, it's negative 128 feet per second. Okay, so that's the information that's given. With this information, we have to find SO, the initial velocity, the initial position. Okay, that's our goal. But looking for SO, in order to solve for this variable, this unknown, we need S of t, we need t, and we need v0. Do we have all that information? Well, v0 is not a problem because we know the initial velocity is 0. So we're replacing v0 with 0, this is gone. And in this equation, this is gone. But we're still missing two unknowns. We're missing the time and we're missing S of t, which we don't have. So what we could do is find the time using the velocity function. We know that v of t is equal to negative 32 times t. Well, v of t, what's the final velocity? The final velocity is negative 128. And that's equal to negative 32 times t times v0, which was, plus v0, which was 0, which we ignored. And now to find the time, we just divide both sides by negative 32. So negative 128 divided by negative 32 gives us 4. So this whole process took 4 seconds for the ball to hit the ground. Okay, so now we have the value of t. This is great. All we're missing now to find SO is S of t, which we have. S of t is the final position, which is we know to be a 0. So let's go ahead and plug that in. And recall t is 4. So we get 0 equals negative 32 over 2, which is just negative 16. T is 4 squared, plus S0, and now we can solve for S0. So this gives us negative 16 times 16 equals 0 plus S0. That's what, 256 feet equals S0. So negative 16 times 16 is negative 256, and if we bring it over, it becomes positive. And that's the height of the cliff. Okay. So let's go look at our final example. So in our last example over here, we have a car which brakes with constant deceleration of 16 feet per second squared. And it produces skid marks of length 128 feet before coming to a full stop. How fast was the car traveling when the brakes were first applied? So pause the video, try to solve this on your own. See if you're able to get the answer. I think it's a good idea to even draw a sketch of the situation. So let's go ahead and do that. So we have a car with constant deceleration. So the acceleration is negative 16 feet per second squared. Okay, so this is our car. Our car starts over here. It's negative because it's slowing down, it's decelerating. So that's another keyword you have to keep in mind. Producing skid marks of length 128 feet. So if this is the initial position as 0, the initial position, we'll call it point 0, and we know at the end this is a distance, let's call it S final, of 128 feet. That's the length of the skid mark. And then before coming to a stop, what do we know about the velocity? Well, the initial velocity is what the question's asking for. How fast was the car going when it started braking and producing skid marks? What's the V final? Well, the V final, it came to a stop. So how fast are you going if you're stopped? You're not moving. So the velocity is 0. So that's information that's given. So you have to really pay attention to keywords like this. It seems like it's irrelevant, but it's crucial to solving the problem. And now, how fast is the car traveling when the brakes were first applied? So it's asking again for V0. So we start off with our formula. You can always just write this one down, but I like to derive it. So I always start off with acceleration, A of t, is equal to negative 16 feet per second squared. So I'm just going to write negative 16, not to use units. Take the antiderivative, giving me negative 16t plus V0. And then taking the antiderivative once more, giving me negative 16t squared over 2 plus v0 times t plus s0. Okay, so this is the equation that we came up with at the beginning of the video, and now we start plugging in the information that we know. So we're looking for v0. We can use the second equation, but in order to use the second equation, we need vt and t. Do we have the vt, the v final? The v final we have, but we don't have time, so we're kind of stuck. That means we have to use the second equation as well. Okay, so let's go ahead and do that. From the second equation, what do we know? We know the S0 is 0. So this is gone. We know that we don't know V0, that's what we're looking for. We don't know time, so we're kind of holding off on this. T we still don't know, and S of t we know it to be, sorry, S final is 128. So we get 128 equals negative 16 over 2 is negative 8 t squared plus v0 times t. This is what we have so far. We still have two unknowns. But the good thing is that the two unknowns that we have here are the same two unknowns that we have up here. That's what you have to catch. So over here, the initial velocity is what we're looking for. We could solve for t. Because we know vt, the v final, is 0. So from this equation over here, we have that 0 equals negative 16t plus v0, meaning that 16t is equal to v0. Okay. So further, what I would do is I would solve for t, so divide both sides by 16, giving us v0, t equals v0 over 16. I'm dividing both sides by 16, and I'm going to substitute my t into this equation. So we get 128, I'm just going to continue up here. We get 128 equals negative 8 times t squared. So negative 8, but instead of writing t, we're going to write what it's equal to, v0 over 16 squared. Plus v0 times t. So v0 times t is v0 times v0 over 16. So it's plus v0 squared over 16. Okay, because v0 times v0 over 16 is v0 squared over 16. And now, what could we do? We could simplify. So we get 128 equals negative 8 v0 squared over, so I'm going to square both terms, over 16 squared, which is 256. Plus, over here we have 16 on the denominator. I'm just going to multiply the top and the bottom by 16 to have the same denominator because we have fractions. So we get 256 on the bottom, and on top we get 16 v0 squared. Okay, so I just multiplied the top and the bottom by 16 to get this. Now that the denominators are the same, we could add the numerators. So we get negative 8 v0 squared plus 16 v0 squared, which is positive 8 v0 squared. So I'm just going to erase this and give myself some room. So we get 128 equals 8 v0 squared over 256. Now we're essentially cross multiplying. Think of this over 1. I'm going to multiply the top by 256. So 128 times 256, we get 32,768 equals 8 v0 squared. Divide both sides by 8. I get 4,096 equals v0 squared. And lastly, we square root both sides, giving us 64. Plus minus 64, but we take the positive. Okay. So we have determined that the final velocity, the velocity of the vehicle, the v initial, is 64 feet per second. So the vehicle was traveling at a speed of 64 feet per second. Okay, and that's the answer. So I hope this video helped, and keep practicing. I'll see you in the next one.